In this video, we're going to look at addition reactions of various carbonyl compounds. We're going to start by a really simple reaction. We're going to take formaldehyde and stick in water, and we're going to look at an acid-catalyzed reaction. So what happens? Well, the proton goes with the carbonyl and gets things rolling by forming this oxonium ion. The oxonium ion goes over here, finds a water molecule, and the water molecule will attack that carbon. Why does it attack the carbon? Well, the whole thing's positive, and it's short of electrons. And that gives us this rather strange-looking species here, which simply is going to lose a proton. And loses that proton. What does that give us? Well, it gives us a very simple molecule, which we simply call a diol. In fact, it's called a gem diol, G-E-M diol. And gem just means two substituents on the same carbon. So here we have an alcohol. There's two OHs on the same carbon, so it's a diol. Now, this equilibrium, it turns out, is quite favorable for formaldehyde. Formaldehyde is a gas, but it dissolves in water. And when it dissolves in water, this is actually the reaction it's doing. So it exists as a hydrate. And the equilibrium constant for this, as I remember, is like 2,000, which just means it's pretty favorable. Now, do other carbonyls do this? Well, if you simply go down and do an aldehyde, it turns out an aldehyde will do the exact same chemistry. Now, I'm using the equilibrium arrow here, emphasizing that all this chemistry goes back and forth. So it's an equilibrium situation. So everything's reversible. And instead of drawing single arrows, I'm just simply drawing equilibrium arrows. So again, this is going to do the same thing. We're going to protonate the carbonyl, okay, form our oxonium ion. That oxonium ion, okay, is going to be attacked by a water molecule on that carbon. Push the electrons over out onto the oxygen. Form our protonated diol, then just drop off one proton and form our diol. Now with an aldehyde, it turns out that this occurs to about it turns about almost equal amounts. The equilibrium constant for acetaldehyde is 1.1, which means essentially 50% of the aldehyde is hydrated and 50% is not. So it's actually kind of funny. Here's this aldehyde. We put it in water. Half of it's not an aldehyde anymore. It's a diol. Turns out that you almost don't even talk about it though, and the reason you don't is it's all reversible. So the aldehyde in water will still react like an aldehyde because even though half of it's over here, it'll swing back and react as an aldehyde through this equilibrium process. What about a ketone? Well, not surprisingly, ketones do the same reaction. But it turns out with a ketone, the equilibrium favors the ketone. And that's simply because the ketone's more stable. And we'll look at this here in a second. Get a proton down here. Need a water molecule. Okay, same routine. You know it by now. We're going to come protonate that oxygen. Produce our there's our protonated. There's our oxonium ion. Okay. We need water. Water is going to attack. There we go. It gets a little repetitive. Lose our proton. And we get our final diol. Now, the equilibrium constant in this case is 0.001. So the equilibrium constants are, 0.001, it's 1.1 for the aldehyde, and it's 2,000 for formaldehyde. Now, why is the formaldehyde so much higher? Well, it's the hydrogen can offer nothing to the pi system. This double bond's electron deficient, and just like alkenes, The more alkyl substituents you have on the pi system, the more stable it is. So formaldehyde has no stability from the pi system at all. Hydrogens don't have any p electrons. You add one methyl group, you stabilize it basically by a factor of 1,000. You add a second methyl group, you stabilize it by another factor of 1,000. So formaldehyde, this equilibrium essentially lies totally to the right. In fact, 2,000 is a huge equilibrium constant. For a ketone, it hardly happens at all. It's only a 1,000th is the equilibrium constant, so it lies completely to the left. So this is the reaction with water and to form these gem diols. Now, if that was all there is to it, it would be interesting, but not terribly exciting. But the fun thing is that you can do this whole reaction with alcohols as well. And let me just erase everything, and I'm going to start over. And this time I'll just do the aldehyde. I'm not going to do them all. You can draw out the other ones yourself. But let me just start off with an aldehyde. And it's an aldehyde, so it has a hydrogen on there. We don't have to draw that. Oops, I screwed that up. We don't have to draw on that hydrogen, but there it is. So again, let's do an equilibrium, but this time let's use an alcohol. So we're going to use let's do ethyl alcohol. So here's come on. Here's my ethyl group. But I still want to be acid-catalyzed, so I'm going to throw in some protons. And let's do the same reaction. So again, it's all going to go very similar. We're going to protonate the oxygen. There's our oxonium ion. Again, I'm drawing these as equilibria because that's what it all is. It's all an equilibrium process. And copy the methanol over here. The methanol is going to attack. Okay, and it's going to look very similar to the diol formation. We just have to now lose our proton, and we've got our final product here. And there is our final product. And in this case, it's kind of interesting because the product here now has one ether linkage and one alcohol, one hydroxyl. This is called a hemiacetal. The word hemiacetal is kind of a funny word. Hemiacetal, and the hemiacetal is it turns out a very common functionality in biology, and it's a very important component of sugar chemistry, which we'll see a little bit later. Now this is half it's an ether and a hydroxyl, but you can keep going because if we're sitting here in acidic methanol, we don't have to finish. I can come in here and I can do a new equilibrium, and by bringing in some more methanol, and indeed there's more methanol and indeed more acid. Okay, I'm going to use the proton again, and of course, what I can do is I can do an exchange here. So let me protonate the hydroxyl group. Okay, protonate the hydroxyl group. Now, what can happen? Of course, that water molecule can leave, and so I can go over here on the oxygen of the ether linkage. Form double bond. I think I put that arrow in the wrong place. Sorry. I think it's pointing to the carbon instead of the bond. You got to be careful about that. Point to the bond. Okay, and that forms a double bond there and pushes out the water molecule. And what we get when we're done with that is we get a new oxonium ion, but now this oxonium ion involves, basically an ether linkage. So this is all susceptible to attack now by another methanol. So I just have to duplicate the methanol. Okay, so here's the methanol, and that can come around and attack the carbon, pushing the electrons back out onto the oxygen. And This will, oh, we're almost there, and lose the final proton. And one more equilibrium arrow, and click. Here's our final product. We just center it. So this is an acetal. So it turns out that if you look at the overall process here, you protonate the carbonyl, get an oxonium ion, add an alcohol, lose your proton, you get a hemiacetal. Then proton out the hydroxyl, split out a water molecule, form a new oxonium ion, attack with another methanol, lose a proton, you form an acetal. Hemiacetal just simply means half an acetal. So we're starting with our aldehyde. If we go halfway, we form half the acetal. If we go all the way, we form the acetal. Now these molecules are interesting because they no longer have protons, of course. They have different physical properties, and but they're turns out to be quite important. Now, equilibrium-wise, this is not so favorable. Partly just entropy is really bad. We're tying up all these molecules, and it turns out that this equilibrium is not as favorable as the diol by any means, so it kind of lies to the left. But as we'll see, that there's some tricks where you can make these favorable, and one trick is actually going to be doing a ring. Let's take a look at the ring formation. So this will be our last one of these we're going to do in this video because I'm getting tired of this. So let's go back to our aldehyde, and in this case we're going to do something a little bit different. Well, that wasn't very nice. Let me try that again. Here's our aldehyde, and this time we're going to use a very special alcohol. I'm going to use we're going to draw out, special structure. Oh, I'm having a terrible time here. Here we go. We're going to use this diol. This is ethylene glycol. This is ethylene glycol. It's what you use as, if you have a car, this is what you use as antifreeze. And again, we're going to do an addition. So the mechanism is going to be pretty much the same, where basically it's kind of repetitive. Protonate the oxygen. Okay. Then bring over our diol. Okay. Do an attack. The oxygen to come over and attack the carbon. Move electrons of that. We're well on our way here. I want to now do a transfer of a proton, and actually I'm going to do a shortcut here. I know I want to lose this OH, so I'm going to have this proton reach this oxygen around here and grab that. Now this is probably in real life 2 real steps, but I'm taking a shortcut. See what I did there? I'm basically just transferring the proton from one oxygen to the other, simply because I know where I'm going. And we'll get this intermediate, and this intermediate is all set up to lose that oxygen of the hydroxyl, or lose the hydroxyl. So I'll use this lone pair to reform an alcohol. I did the same thing as I did the last time. I pushed the arrow to the wrong place. So let's go here to the bond. Okay, kick out the water, and we're on our way. Okay, let me center this. Well, it's a little bit, just move it in a little bit here. Okay, and now in this case, all we have to do is cyclize. So this oxygen simply swings around, attacks that carbon, goes there. We're getting close. And look at that. We formed this really nice ring system. Okay, so this down here is a cyclic acetal. So it's an acetal, but it's cyclic. And these cyclic acetals are quite stable. And why is it more stable? Well, again, it's partly an entropy, because what are we doing here? When we're starting with an aldehyde and alcohol, we're starting with 2 molecules, and in this whole reaction, we split out a water molecule and this. So we start with 2 molecules, we get 2 molecules. Whereas if you had 2 alcohols, you start with 3 molecules and you get 2 molecules. So entropy is basically neutral in this one. It's purely the enthalpy of it, and the enthalpy-wise, this is not bad. So this is actually a fairly stable system. But it's an equilibrium back and forth. And how would you control it? What you do is you control the relative amounts of water and the ethylene glycol. If you have no water and you add protons to ethylene glycol, you'll force the equilibrium to the ring here. If you start with a ring, add protons and some water, you'll open it back up and go back to the aldehyde. So you can force this thing in either direction depending upon conditions. Aldehyde plus the diol will go to the ring, take the ring, the cyclic acetal, and protons in the presence of some water, and you'll go back to the aldehyde. And this turns out to be a really useful reaction. And the one way it's used is that you can actually use this reaction to form what we call a protecting group for the aldehyde. So imagine that you had an aldehyde, and somewhere else in the molecule, it wasn't just acetaldehyde, somewhere else in the molecule, oh, I don't know, perhaps you had a bromide over there, and you wanted to convert that bromide to a Grignard reagent. Well, you couldn't do it if you had a carbonyl in the molecule. But if you did this reaction first, you could hide that carbonyl. And let me show you what I'm talking about. Is let's say we had this molecule here, okay, where we have an aldehyde, okay, and over here we have a bromide. Now, what you'd like to do is make the lithium reagent of this molecule, our Grignard reagent of this molecule. We can't possibly do it because the Grignard will immediately react to that carbonyl. But if you do this reaction first, okay, you take this, I'm not going to draw out the whole mechanism, but if you take this whole diol, okay, and you take some protons, take some protons, okay, what you will make, okay, when you're done here is you'll add that cyclic acetal. Let me grab a 5-member ring. Oops, sorry. Having a terrible time. Okay, now I've got it. You've got that 5-member ring, and here's your product. And the point is, now you could take this thing and you could react it with say a lithium reagent. Or lithium, I'm sorry, we said Grignard, right? I mean magnesium. Okay, you could do lithium as well. And you could make your Grignard reagent. And not worry about the presence of the carbonyl. Because if you tried to do that Grignard reagent when you still had the carbonyl, it would immediately react. So you can now go ahead and do some chemistry with this. And then when you're all done, what you do is you throw in protons and water and just go back to the aldehyde. So it's a way of hiding the aldehyde from the Grignard reagent. So this is really, really useful chemistry. So I'm going to end there before I confuse you anymore. And you'll have some problems to work on this after the video.